So now let's think about a more interesting case for a natural coordinate system. We're going to now do a natural coordinate system which is not just polar or Cartesian. So this is natural coordinate systems part 2. Um, and I think the example that we'll choose is maybe one that I've seen for some mods and projects before. It's the zip line example. So you imagine that you have a sort of zip line. So it's some straight line here connected between 2 points. It's maybe at some angle, and hanging off of the zip line is some person, and we'll abstract that person to basically be sort of a person that's hanging from some string at some distance. So they're basically a mass on the end of a string. Obviously, there are other ways that you could choose to abstract it, but I'm going to choose that abstraction. So what's the right coordinate system to define this? Well, if you think about it, certainly the only thing that it initially seems like you need to know is this location, right? If you know where that mass is, then everything's good, right? Well, not really, because you actually need to know this location as well in order to figure out what the direction of that force is. There's a constraint that the distance between the sort of carriage here, and I'm going to assume there's some kind of carriage connected there, and the center mass of the rider is, there's some distance there, and that distance is a constraint. Okay, so what would the right natural, how many variables do you need to describe this, and what would the right coordinate system be? Well, pretty clearly one thing you would want to know is what this distance is that the carriage is along the rail, right? Another thing that you might reasonably want to know is what the angle is that this guy is hanging at. Let's define that angle as from the string, from the rail, or from the wire or cable or whatever the hell it is. So if I had those two things, would I know everything about the system? I think I would. I would know where the carriage was, right? That's what D tells me. And notice that the carriage can only be along that cable. And I also would know where this mass was, because as long as I know that angle, I'm assuming that I know this distance is some distance L, which is just fixed. Okay. All right, so it seems like those two coordinates, D and theta, would tell me what where the system is, right? And I only have two. That's a pretty small number. Like one is the only option that's lower than that, and pretty clearly there's no way one variable alone is going to tell me where both this is and this is, because they could both be at different positions relative to each other. Okay, well, once I've done that, now I need to think about how do I actually express things in this coordinate system, because it's not the same kind of coordinate system we've used before. We already know r hat and theta hat and I hat and j hat. How are we going to think about this? This is where we start to use some of the unit vector ideas that we've expressed earlier. So let's think about that. One direction that's an interesting direction here. So let's identify the interesting directions. One interesting direction is what I will call the d hat direction. Okay, what d hat is a unit vector that points along this rail. Okay? It's an interesting direction from a couple of perspectives. One way it's interesting is if there's like friction acting at this on this carriage, that's going to be acting in the d hat direction. So d hat is a pretty important unit vector, and if I actually think about where this carriage is located, I could say that the position of the carriage is simply d times d hat, right? That's pretty straightforward. What about the position of the mass? Well, or of the person? Well, I need another unit vector. I pretty clearly can't get there just with d hat. One option would be to say, okay, well, this sort of looks like a polar coordinate system acting about this point. So what if I call this direction r hat, right? And that direction theta hat? Well, then I could say that the position of the person is what? Well, it's tempting to say the position of the person is simply L times r hat. That's a little bit problematic. And the reason it's problematic is that we actually need to decide, we already decided what our origin was in the system as soon as we talked about what our carriage was. When we said our carriage was d times d hat, we actually were saying our origin is located here. So if we actually want to know what the position of the person is, we need to know what the vector is that goes from the origin to the person, in the same way that the position of the carriage is the vector that goes from the origin to the carriage. So really the position of the person is actually our carriage plus L times L hat. So at this point you have a really nice clean way of talking about what the system's configuration is, right? You have two directions, actually really three directions that you'll end up worrying about, r hat, d hat, and theta hat. But when you say that our person is our carriage plus L times r hat, that actually means something fairly, it's a very compact and easy to understand way to express what the location of the person is. Notice I have not got any sines or cosines or any of that stuff in here. It's all very compact inside of r hat and inside of d hat. Okay? Now this will allow me now to be able to do a lot of powerful things. Like for example, if I want to figure out what the velocity of the person is, how am I going to do that? Well, the velocity of the person is simply d by dt of the position of the person, right? And the position of the person is the position of the carriage plus L times r hat. So it's d by dt of r carriage plus L times r hat. Well, r carriage is simply d times d hat. Well, d hat is a unit vector that just points along this cable. D hat never changes, right? The direction of the cable is fixed, assuming, I mean, we're not dealing with sag in the cable. That would make our lives a whole lot more interesting. But since d hat is fixed, the only thing that can change here is d, right? So it would be d times d hat plus L times r hat. So we get d dot times d hat, right? How fast is the carriage moving? And then plus d by dt of L times r hat. Well, r hat is still a polar type of definition, right? R hat is going to have a component that has to do with how much is in the d hat direction. It will also have a component that has to do with how much is in the sort of perpendicular to d hat direction. But all of the derivation that I've done previously for polar is still going to apply to this d hat. So I actually can immediately write L times theta dot times theta hat. Now, I'll warn you at this point that there's something that is fishy and funny about this coordinate system. And the way that I'll warn you about that is by asking you a question and asking you to think about this, and then I will end this video. What is r hat dot d hat? And how does that contrast with a polar coordinate system where r hat dot theta hat is something, or a Cartesian coordinate system where I hat dot j hat is something? So there's an issue that's embedded in here that needs to be thought about, but we'll come back to that later.